All right, today we're talking about behavior of polynomials, kind of their intro to graphing polynomials. So a lot of this, yes, we can get by just graphing with the graphing calculator, but it's important to understand parts of our graph and what we can get from our equation. So I've loaded in an example over here, and there's a couple key parts that we'll want to look at today. So the first one is called the degree, which we've already looked at, right, when we were naming things. This is the degree of our polynomial. And a degree 3 polynomial tells us we have 3 solutions total. They could be real, they could be imaginary. And it also means we cross the x-axis up to 3 total times. Okay, so we could maximum number of times we cross the x-axis would be 3 times. It might be less than that. We'll see. Okay, next up we have the leading coefficient. So in front of my highest degree term, which was x to the third, the coefficient or number in front is called our leading coefficient. And what that tells us is whether or not the right-hand side of my graph is going up or down. Okay, so if this is positive, the right-hand side of my graph will rise, and if it's negative, it will fall. It will go down on the right-hand side. So the very right-hand side of my graph, the sign of my leading coefficient, whether it's positive or negative, will tell us which way it's going. And lastly, from our equation, we can look at the very end. And the constant at the end, okay, when our polynomial is in standard form, is our y-intercept, where my graph crosses the vertical axis, the y-axis. Okay, so we actually know a lot of stuff about this graph. Okay, so to reiterate what we talked about here, the leading coefficient describes the very end behavior, so as we go very far to the right-hand side of my graph. Okay, specifically, if it is a positive number, if my leading coefficient is positive, the right-hand side of my graph will go up. Okay, I don't know what's happening on the left. It could be, going down. It might also be going up. I don't know, but I know the right-hand side, okay, is going up. So one of the ways we notate this is called limit notation. This says as x approaches positive infinity. So think about our graph where our positive numbers go to the right and up. So as x, the horizontal, goes towards positive infinity as we go to the right on our graph. That's what this is describing. F of x, which is y, my function, is going up. It approaches positive infinity, so we're going up towards the positive numbers. So as x goes to the right, y goes up. As we go to the right on my graph is going up. It's kind of what this describes. Okay, so we've worded that down here. Okay, if I get a negative leading coefficient, we know the right side is falling. Okay, again, I don't know what's happening on the left side necessarily yet. It might be rising. It might also be falling. Okay, but I know the right-hand side is definitely falling. Okay, so the right-hand side is definitely going down. And this says as we go right on my graph, my function is going down towards negative infinity, right? So as we go to the right, my graph is going towards the negative numbers. It's going down on the right. Okay, again, the degree, which we talked about back up here in blue, tells us how the left and right end behave when we compare to each other. Okay, specifically, if I have an even degree function, so if it's degree 2, or degree 0, or degree 4, or 6, or 8, any number, if the highest power is even, the left and right hand side will go the same direction. So think about, for instance, x squared, right? We had parabolas that opened up or opened down, but they were either both going up or both going down. The left and right behaved in the same way. That's true about x to the fourth, x to the sixth. They're either both going up, the left and right hand sides, or both going down. There could be all kinds of crazy stuff happening in the middle, but I know at the extreme left and right, all even degree polynomials either both go up or both go down. If it's an odd degree, like the one we had above, the left and right side will go in opposite directions. So if it's an odd degree, say x cubed, one might be going up and the other is going down, or vice versa. Maybe the left side is going up and the right side is going down. Okay, so it could kind of be either case for these. There might be all kinds of weird squiggles and things happening in the middle, but I can tell you what's happening at the extreme ends. They're going up or down. Odd degree functions always go in opposite directions. Even degrees always go the same direction. And remember, we can basically figure out which direction by looking at the leading coefficient. If I know what's happening with the right, and then I know the left is doing the same thing, hey, I can figure out what both sides are doing. Or if I know what's going on the right, and I know they go in opposite directions, we can figure out what the left is doing as well, right, with a little bit of deduction. Okay, so let's use these ideas. It says describe and sketch sketch the end behavior and identify the y-intercept. So let's look at first our degree. This is an odd degree function. And that tells me my tail ends go in opposite directions. So if the right's going up, the left's going down, etc. So they go in opposite directions. And then we're going to look at our leading coefficient, which is -2. And that tells me the right side, specifically, goes down. Oops, that's supposed to be a W, down. Okay, so if I know the right side's going down, and they go in opposite directions, well, then the left side needs to be going up, right? So the left side would need to be going up. So the left side goes up, the right side goes down. Right side goes down again because that's negative, and they go in opposite directions because it's odd. So there's our sketch for end behavior. Then it wants me to identify our y-intercept. And so we do have a nice constant at the end. So my y-intercept is the point 0, -5. Okay, let's try our next one. B. And again, we can kind of look at the degree and leading coefficients. So here's my highest degree, which is even. Remember from the previous slide, even degrees go the same direction. So these go the same direction. They're either both going up or both going down. Okay, then we can look at our leading coefficient. In this case, we have a hidden +1. The +1 says our right side goes up because it's positive. So we're just looking at the sign there. The right side goes up. So if the right side's going up and they go in the same direction, then the left side must also be going up. And again, I'm not exactly sure what's happening in the middle, but I know it's smooth and continuous and there's nice curves, but I know the left and right side are definitely both going up for that graph. And so here is my y-intercept. Ooh, notice there is no constant. And if we're missing a constant, we can think of it as being 0. This graph goes through the origin, 0, 0. That's where we'd write our y-intercept. Okay, our next one. This one, try these next two out, I would say, actually. So pause the video now, see if you can figure out roughly what directions they're going in and what our y-intercept is for C and D. All right, here we go. For C, you should have come up with they go in opposite directions. It is an odd degree function. My leading coefficient was positive, so the right side went up. And since they go in opposite directions, the left side must be going down. We also did have a constant, +4, so my y-intercept is 0, +4. For D, should have come up with they go in the same direction and that the right side goes down. So if the right side goes down and they go in the same direction, they're both going down. Okay, my y-intercept here, we did have a constant of -1, so 0, -1. Okay, again, these can all be checked with Desmos just to show, right, what's happening on the left and right-hand side by just graphing them as well. The next thing we're going to talk about is what's called the multiplicity. Okay, multiplicity is the number of times an x-intercept, also called a root or 0, is repeated. So let's say if we're solving something and we get the answer 2 twice, that would mean we have a multiplicity of 2 because it's repeated twice. It's the number of times an answer is repeated, essentially. Okay, so a couple odd things that happen here, I guess pun intended. If it's an odd multiplicity, so it repeats itself or it's we get that answer back 1 time or 3 times or 5 times, my graph will cross the x-axis. So if this is the x-axis, okay, if this is our x and y axis, an odd multiplicity in my graph might just pass through. Okay, it's just passing on through. It's just going to cross the x-axis at whatever that value is. Okay, however, if we get an even multiplicity, my graph actually bounces off the x-axis. It does not pass through to the other side. Okay, so if we had a graph with an even multiplicity at this value, say -1 or -2, whatever that would be, it might come from the top or bottom and it kind of hits that point and turns around. Like it doesn't pass through to the other side. Okay, so anytime it's repeated an even number of times, we'll see it kind of deflect off or bounce off the x-axis. It will stay on the same side. All right, so here's our first example. So this is in what's called factored form. So there's some good and some bad things about factored form. The good things is it'll be very easy to find our zeros and their multiplicity. So we can kind of go straight to finding our zeros. If we set our function equal to 0, this is x minus 3, this is x minus 1. Ooh, there's 2 of them. So we're actually just going to write that out, times itself twice, and x plus 4. And if we set all of these equal to 0, we can find the zeros. So we'd say x minus 3 equals 0, or x minus 1 equals 0, and then or x minus 1 equals 0, and then x plus 4 equals 0. And so if we solve all of these equations, by adding 3 over, we should get positive 3. By adding 1 over, we get positive 1. By adding 1 over again, we get another positive 1. And by subtracting 4 here, we get negative 4. Okay, so for our solutions, we get 3, we get 1 twice, and then we get negative 4. Okay, so we can list our zeros and their multiplicities in our box here. So let's start with the smallest 0, because we'll kind of work left to right on our graph. Our smallest 0 is negative 4, and it only occurs once. Remember, that's our multiplicity, how many times it occurs. Our next smallest number is positive 1, and that does occur 2 times. It has an even multiplicity. And 3, our biggest number, only occurs once. So we know a few things about my graph. It's going to touch the x-axis at negative 4, positive 1, and positive 3. Those 3 values. However, it's going to cross at negative 4 and 3 and bounce off the x-axis at 1 because it's an even multiplicity. Okay, odd multiplicities, it will pass through. Even multiplicities, it's going to bounce off, either stay above or below. Okay, the other things that we don't know yet, we don't know the end behavior, and we don't know our y-intercept. Okay, now we could spend all of our time multiplying all of that mess together. That would take forever. Okay, so instead, what we're going to do is take the largest term in each. So our biggest power of x in each of these. So x times x times x times x. You can even imagine there being 1s in front of these. 1x times 1x times 1x times 1x gives me 1x to the 4th power. This would be our leading term, the biggest possible term I would get if we spent our time multiplying all of that out. And I'm really only interested in the very first and very last term for my end behavior. So this would be our leading term. It gives me the degree. It's degree 4, which is even. And so that means the tail ends of my graph go the same direction. My leading coefficient is positive 1, which means our right side goes up. So we know a few things about my graph already. The right side goes up, and they go in the same direction because it's an even degree function. So if the right's going up, the left must also be going up. So we have some sort of rough sketch for a graph that looks like this. Now we can also find our y-intercept, if we like, by looking at all of the constants of every term and multiplying them. However, I think that's going to take us out of our graphing window, but if we wanted to know, negative 3 times negative 1 is positive 3, times negative 1 is back to negative 3, times 4 is negative 12. My y-intercept would be 0, negative 12, which, is somewhere towards the bottom, like a little off the screen, right? Probably somewhere down there. Okay, so not nicely in my graphing window this time. Maybe I'll try to make my graph look like it goes down there. We'll see. Okay, but I have enough to sketch in my graph. I know we're going to come in from above to the left of my first x-intercept, right? Our first 0, negative 4. So we come in from above, and as I start to approach it, I look at its multiplicity, and because it's odd, we're just passing on through. Maybe I'll make this look a little more steep so it looks like it's heading down towards our y-intercept of negative 12, right? Okay, so supposedly this goes to our y-intercept. You don't necessarily have to be that accurate if it's out of your graphing window, but we'll pretend that that's nicely connected there and there. Okay, and then we're going to curve back up to my next 0 of 1. But notice this one has an even multiplicity. So what that means is when I get up here, it's going to bounce off the x-axis, and this should look more like a function. It's going to bounce off at positive 1, not pass through. Then it's going to start to curve back towards 3, which is pretty close, so I don't want to go too far down. And I notice that 3 has an odd multiplicity, so it's just passing on through. And so we get a function that does roughly something like this. Now, how low you make this kind of, valley in both of these, it's kind of up to you. We're just hand sketching it. I'm not going to make you find every point in between. That's just borderline child abuse. Let's take a look at the actual graph, though, using Desmos and see how close we were. Okay, here's my graph in Desmos. And we can see right here, yes, it's passing through at negative 4. It's bouncing off at positive 1 and passing through at positive 3. And in fact, we can even see down here, yep, there's my nice y-intercept at negative 12. Pretty good. When we compare that to our sketch, obviously it's a little off, but we did pretty good. It's rising on the left and right as we thought. It's following all the things, our end behavior and our multiplicity and zeros. Okay, let's do one more example. Of course, we'll do more of these in class. Find all zeros, and then again, use multiplicity and end behavior to sketch your graph. Okay, so first thing, let's write these out. That's what they really mean. This is like negative 1 times x, right? Even x squared, you can think of as x times itself twice. Then we have x plus 1 cubed, which means times itself 3 times. Whew, it's a lot of writing out. But we only have 1x minus 2. Okay, so here's this thing factored all the way out. Again, this is in factored form. And we can set each one equal to 0. Well, negative 1 is never going to equal 0, but we would do this for our variables. Either x equals 0, x equals 0 again, x plus 1 equals 0. I can write that. Or x plus 1 equals 0. Right, we would do the x plus 1s 3 times, which is going to give me the same answer 3 times. And then x minus 2 equals 0. Okay, so all of our solutions subtracting 1 here would give me negative 1. This gives me the same answer, and this gives me the same answer. Adding 2 over gives me positive 2 here. And of course, each of these is the same thing, x equals 0. So listing our solutions out, we get 0 twice, we get negative 1 3 times, and positive 2 once. So our smallest numbers, I fill in the table here, furthest to the left would be negative 1, which occurs 3 times. It has a multiplicity of 3. 0, our next biggest number, occurred twice, an even multiplicity. And positive 2 occurs 1 time. So it's an odd multiplicity. So a few things we know about my graph. It's going to touch the x-axis at negative 1, at 0, and at 2. At 0 and at positive 2. Okay, so it's going to touch at those 3 points. Okay, let's find our end behavior by finding our biggest degree term. So we need to take the biggest term in each, and we're even going to use our factored form here. So negative 1 times x, that's negative 1x squared, times another x, negative 1x to the third, negative 1x to the fourth, negative 1x to the fifth, negative 1x to the sixth is what we'd end up with if I multiplied the outside here, and if there is a term on the outside with no parentheses, we multiply that by the 1x here, the 1x here, here, and here, and we end up with negative 1x to the 6th. So this is an even degree polynomial, which means the tail ends go the same direction. So they're either both going up or both going down, and we look to our leading coefficient, which says the right side goes down because it's negative. Okay, so if they go the same direction and the right side's going down, then the left side is also going down. Okay, because they go the same direction. So now I have an understanding that as I go to approach my first 0, negative 1, we're going to be coming in from below. So coming in from below towards negative 1, and I look at the multiplicity, and because it's odd, remember odd multiplicity, it's just passing on through. It's just passing on through. Okay, next we get a 0 of 0, and it's an even multiplicity. So as I curve back towards 0, this guy's going to bounce off the x-axis and stay above. As we go to approach the next one too, it's an odd multiplicity, which means we're just passing on through again. Now you might have noticed this time I didn't go find my constant, my y-intercept. Now if you did that, you still have to take the smallest term in each, which would be negative 1x squared times 1, which is negative 1x squared, times another one, which is still negative 1x squared, times another one, which is still negative 1x squared, times negative 2, which is positive 2x squared. That is the smallest term we could make, which means there is no constant. This kind of x squared on the outside kind of guarantees there won't be a constant. So my y-intercept was actually at 0, 0. And in fact, if I get a 0 of 0, that's both an x and a y-intercept. So we've kind of already solved for that. So here's my graph. Our tail ends are both going down, just like we thought. It's bouncing off at 0, passing through at negative 1 and 2. Let's take a look at Desmos and see how we did. Okay, I really had to zoom in on this one. It almost looked like it was going to touch the x-axis again, but I think it's giving us a local maximum point in that kind of curve there. So it comes up, it goes through negative 1, stays above, bounces off at 0, goes up, in this case pretty high apparently, comes back down, passes through 2, but our left and right hand side are both going down, and we have the proper things happening at our zeros.